Hi! Today's lesson is about the pH and pOH concept. Let's start with pH. Most people like to describe pH as the potential hydrogen. We will define it mathematically towards the end of the lesson, but to start things off, we'll think of it in this fashion. Potential hydrogen. Hydrogen, we've learned, when it's in its ionic form, is indicative of an acid. So another way that people like to think of pH is that it's telling us how acidic a substance is. We also have the pOH concept. Similarly, one can think of pOH as meaning the potential of hydroxide. We know that hydroxides are the OH -1 polyatomic ion, and they are synonymous with bases. So another way to think of the pOH scale is it tells us how basic a substance is. Some general properties of acids. They tend to be sour, and they tend to react with metals. You may see warning labels called corrosive on acids because that means they tend to react with metals. Some general properties of bases. They tend to taste bitter. If you've ever used a toothpaste with baking soda, you know that's a bitter taste. And they tend to be slippery. Soaps and cleaning agents are substances that are basic in our everyday life. And when you think about how Windex or Pine Sol or soap feels, it tends to be slippery. Well, now that we know that there are two different ways for us to talk about acids and bases and how acidic or how basic a substance is, let's get into how this is done. Acid-base detection. How do we know whether a chemical is going to be an acid and a base? Or a base, excuse me. In the laboratory, we're going to use things called indicators. Some of them are solutions themselves. Other indicators are paper that we can dip into the chemicals. We are going to hyper-focus right now on the paper indicators that can help us tell whether or not our chemical is an acid or a base. The first type of paper is called litmus paper. And maybe you've heard in everyday vernacular that, we need something to pass the litmus test. This is a really quick way to test whether something is an acid or a base. And there are two types of litmus paper. One type is red, the other type is blue. If your red litmus paper stays red, that means your chemical is an acid. If your red litmus paper turns blue, that means your chemical is a base. The association here, base and blue, both start with the letter B. That's an easy way to remember which color litmus paper indicates acid and base. If we started with blue litmus paper, it too can change colors. It can change to red or it can stay blue. If the blue litmus paper winds up changing color to red, it means our chemical is an acid. And if the blue litmus paper stays blue, it means our chemical is a base. Let's look now at the images. This illustration or graphic, what I'm putting in the purple box here, is showing you blue litmus paper turning red when it's dunked into the solution, and red litmus paper turning blue when it's dunked into the solution. Based upon our notes, though, the litmus paper can still stay the same color. And I wanted to show you what the litmus paper looks like in real life, because red litmus paper really looks pink, and blue litmus paper really looks purple. However, they're called red and blue, respectively, despite the fact that they look pink and purple. Now, if the pink paper just looks like it got wet, that means that it's ending up red. So red stays red. The picture, again, that I'm putting in the purple rectangle shows the pink paper turning blue. And anytime, whatever your color ends up, if it's blue, it's a base. If it ends up red, it's an acid. So if we look now at the highlighted picture here of my unknown, the demonstrator is holding a piece of red litmus paper, and it wound up turning to blue. What does that tell me about this chemical that looks like water? However, I'm going to describe it as a clear, colorless solution. Because red ended up blue, if your paper is blue, that means you have a base. This is some type of base. More likely than not, it's going to have those hydroxide ions floating in the solution. That's what we mean by a base. There is a second type of paper. If we come back to our little flow chart here. The second type of paper is called Hydrian or pH paper. It's orange in color, and the only way to tell whether we have an acid or a base is comparing it to the pH scale. I'm changing to green ink now, and I'm coming to the illustration, and I'm showing you this universal pH or Hydrian paper. Hydrian's the brand name. It's like calling tissue Kleenex. Puffs makes tissues, Stop and Shop makes tissues, but if someone said, "Oh, can I get a Kleenex?" you would know what they meant. Hydrian is the brand name. The pH paper is the generic word. Looking at the paper, notice that it's orange in color to start with. And when you dunk it into the solution, it's going to turn a color. And that color then has to be compared to the scale that comes with the paper. It's also known as the pH scale, and you match the color. Notice that each color has a number. That number correlates to the pH scale. Looking at this particular illustration, the orange paper turned kind of navy bluish. In real life, you'd be able to take that piece of paper and literally hold it up to the different color squares or rectangles on the scale so that you're able to get the best match possible. Eyeballing it though, it looks somewhere up here in like the 13 or 14 range. I think the 12 is just a little too light. So you would match the color of the pH paper to the scale that comes with the packaging, and then you get a number. And that number is going to correspond to numbers on the pH scale, which brings us to our next image. The pH scale. Now notice the P is lowercase and the H is capital. That is not a typo. That is how the symbol pH is abbreviated. You'll notice that the pH scale comes in a number line. Its lowest number is 0 and its greatest number is 14. And because pH is basically telling us how acidic or how basic something is, notice that we have those two terms, acidic, and we have alkaline, which is the same thing as basic. The midpoint between 0 and 14, which is 7, our midpoint, is considered to be neutral. It's the midpoint between acids and bases. When we think about the substance in our world that has the component of an acid and the component of a base, aka H2O or water, it makes sense that water is the only neutral substance that we have in our universe. And again, that's because it's the components of an acid and it has the components of a base. When you write H2O or water as HOH in this fashion, the H, which is the acidic part, comes first. In other words, anything that's an acid is going to come before the number 7. When you write the formula for water as HOH, the basic part, or the hydroxide ion, is written second. In other words, it's going to come after the number 7. So pH values less than 7 are acidic, pH values greater than 7 are basic or alkaline, and pH values equal to 7 are neutral. The only substance in our existence that's neutral is water because it has the components of the Arrhenius acid and the Arrhenius base. We mentioned earlier that there's the pOH concept. Looking at the next image, you'll notice that pOH and pH scales both have number lines, maximum value of 14. As we look at our colors, which is analogous to the litmus paper, the red is meant to represent our acids, and the blue is meant to represent our bases. Again, the pH scale we just reviewed, the low numbers are acid and the higher numbers are base, because when you write the formula HOH by the number 7, the acid part comes before 7 and the base part comes after 7. If, however, we're switching it And I now want to measure the potential of the hydroxide ion. Now everything gets reversed. Now our lower numbers need to be affiliated with a base, and our higher numbers need to be affiliated with an acid. At this point in time, let's start to dive into the math behind it. So up until now, we've defined pH as the potential of hydrogen, or it's telling us how acidic substance is. The true definition of pH is that it is equal to the negative log in base 10 of the hydrogen ion concentration. Let's get these symbols. The brackets mean concentration in molarity. Molarity is moles per liter. And that's always the case moving here on out. Anytime you see some symbol in a bracket, it automatically means the concentration in molarity. pOH, its actual definition, is to measure the negative log of the hydroxide ion concentration. Notice that they're measuring basically the opposite of each other. Log base 10. Let's come to this graphic here. We'll come back to the formulas in just a moment. Log base 10. If I look here at this concentration value of 1 times 10 to the negative first, that would be the hydrogen ion concentration. If I take that now and substitute it into my formula, the negative log of the hydrogen ion concentration, you are welcome to use a calculator. However, I want to remind you that log is asking what power is 10 raised to. So if I rewrite this as negative 1, because the power that 10 is being raised to is negative 1, the negative of a negative is a positive. Notice that this concentration of hydrogen ions being 1 times 10 to the negative first, that matches up with a pH value of 1. If I repeat that again for a different concentration, let's jump up here. 10 to the negative fourth. That's the concentration of my hydrogen ions because I'm measuring the pH scale. If I now correlate that to pH, the formula for pH is the negative log of the hydrogen ion. In other words, I'm taking the negative log of 1 times 10 to the negative fourth. Log is asking us what's the power of 10. In other words, to the negative fourth, the negative of a negative is a positive. This concentration of 1 times 10 to the negative fourth correlates to 4 on the pH scale. Notice that if I simply changed my concept here and said that now I'm doing pOH, if I wanted to take the negative log of that concentration times 10 to the negative first, my pOH would be the negative of the negative 1, and pOH would be 1. To summarize this, when you have a high concentration of ions, and I'm not going to specify whether it's hydrogen or hydroxide because it's the same, you have a low p-value. So again, if you have a high concentration of hydrogen ions, you'll have a low pH. If you have a high concentration of hydroxide ions, you'll have a low pOH value. How is it that these are related? Well, if I take the pH and pOH values and add them together, it'll give me the value of 14. Where does that come from? It comes from water. We know that water breaks down into the hydrogen and hydroxide ion. It doesn't do it a lot. It does it to a very small extent, and that's called the Kw. It's equal to 1.0 times 10 to the negative 14th, no unit, at the standard temperature at which chemical reactions are done. That's 25 degrees Celsius. This Kw is telling me what the concentration of each of my ions are in this process. Let's do a little algebra. Well, this Kw is a constant. It's 1.0 times 10 to the negative 14th. Again, no unit. What I want to do now is figure out what's the concentration of the ions. Well, if I use X as my variable, and I don't know how many hydrogen ions there are, I'm able to use the same variable for the hydroxide ions because they're in a one-to-one stoichiometric relationship. Another way to write that is 1.0 times 10 to the negative 14th is equal to x squared. To solve for x, I have to take the square root of both sides, and I come up with the number of 1.0 times 10 to the negative 7th. Since x is a molarity, right, I'm trying to really solve for the concentration of hydrogen ions and the concentration of hydroxide ions, I'm going to now include a unit for molarity. The K, that value does not have a unit. However, when I'm solving for the concentration of the ions, I will add the unit of molarity. Let me now take this number and calculate what the pH of water is. Well, pH by definition mathematically is the negative log of the hydrogen ion concentration. That's the negative log of 1.0 times 10 to the negative 7th. Log means to what power is 10 raised to? It's raised to the negative 7th, and the negative of a negative is a positive. So the pH of water is 7. Let's redo that math, now calculating for the pOH of water. pOH is defined as the negative log of the hydroxide ion concentration. I just calculated that the hydroxide ion concentration is equal to the hydrogen ion concentration, which is equal to 1.0 times 10 to the negative 7th. Log is asking me to what power is the 10 being raised? The negative of a negative is a positive. So here we have another justification as to why pH of 7, it's a terrible circle here, is considered to be neutral, because when I'm measuring the pH of water and the pOH of water, because those ions of acids and bases are equal to each other, they have the same concentration, then the p values are going to be the same, 7. And if I add 7 plus 7, that gives me 14, which explains how we derived the pH plus pOH equals 14 equation. To sum up the math, I have a graphic for you here. Some of you may love it, and others may hate it. To clean up our notes and to wrap things up, let's just jot down on the side here all the mathematical definitions we've come up with. First, pH is equal to the negative log of the hydrogen ion concentration. Second, pOH is equal to the negative log of the hydroxide ion concentration. we learned that pH plus pOH will always sum up to equal the number 14. We learned that Kw is a constant that's always equal to 1.0 times 10 to the negative 14th. And that's going to be equal to the product of the concentration of the hydrogen ions times the concentration of the hydroxide ions. These four formulas are going to be used interchangeably to allow us to go between acid and bases. This graphic, for those of you who would like to use it, may be a handy-dandy way to help you figure out how you're going to transition from pH to the hydrogen ions to the pOH, etc. Gives you like a pathway. Whereas others will just look at these formulas, realize where the variables are, and just start to use different combinations of them for solving problems. One last caveat before we end. The math with regards to the logarithms was done in our head because all of our concentration values were 1 times 10 to some power. When you have the 1 times 10 to a power, then you can do the math in your head. When you get to something that's like 1.2 times 10 to a power, now you're going to have to use your calculator. Because we can have things, for example, such as pH equals 8.7. If I were to undo this, pH is equal to 8.7. We know that pH is equal to the negative log of the hydrogen ion concentration. I know that 8.7 is the power that 10's raised to. So this is like saying 1 times 10 to the negative 8.7th power. We can't leave our answers like this. Reason being, because we can't move the decimal point. (8.7) places to the left, because that's ultimately what a power of negative 8.7 means. So we're literally going to have to type into the calculator 1 times 10 to the negative 8.7 power. Getting out my calculator now. And we wind up with 1.99526 times 10 to the negative 9th power, which rounding would be 2.0 times 10 to the negative 9th. So again, some of the math can be done in our heads. However, sometimes we're going to need to use the calculator. And only when our concentrations are 1 times 10 to a power or our pHs are whole number can we do the math in our head. If our concentration is anything but 1 times 10 to the power, we have to use a calculator. And if our pH has a decimal, we have to use a calculator.